today we're going to be doing a Hess's Law question. So we're going to be working on Unit 3, Question 3. So our question is, use the given equation to determine the enthalpy change for this reaction. So let's start. What is enthalpy change? So our overall enthalpy change is going to be our delta H. So we want to take a Hess's Law as if you add two or more equations to get an overall equation. And once you get that overall equation, you can then add your enthalpy changes to get your overall enthalpy change for this reaction. So this is the reaction that we want to get by the end. And these are the two reactions that we're given. So what we're going to do is we're going to add them together. But if you see here, we have some extra things that aren't in this equation. And we have things that are on the opposite sides that need to be switched. So how are we going to do this? So if you have two identical substances on opposite sides, they'll cancel out. So that's our first problem here. So we have two identical substances, but they're not on opposite sides of the equation, nor are they in the final equation. So we have to get rid of them somehow. And as I said, if we move them to opposite sides of the equation, then we can cancel them out and they'll be gone. So how are we going to do this? First off, what we can do is we can look at our final equation and we can say, how can we change this equation? How can we change these two equations to match this one? So if we see here, we have 2 SO3 gas. And right now, we only have 1 SO3. Now, these are on opposite sides of the equation, so what we're going to do is not only times this whole reaction by 2, we're going to times it by -2. And when we times it by a negative, that will reverse the reaction so that this SO3 is now going to be on the product side, or on the reactant side, and all of this is now going to be on the product side. So we're going to switch them. Now with this one, this SO2 is on the right side of the equation, which is good. And as we can see, there's a coefficient of 2, but in this one we don't have a coefficient of 2. So what we're going to do is we're going to time this whole equation by just +2. When we times it by a positive, it stays in the same direction that it's already in, but when we times it by a negative, this equation is now going to be reversed. So if we times this whole equation by 2, we now have to change this to times it by 2 as well, because this is the energy change of this specific reaction. So this goes by 2, this must increase by 2 as well. Now the same thing goes with this one. But because we're timesing it by -2, we have to times this as well by -2. What this does is, just a little refresher, if we do a negative times a negative, it will equal a positive. So timesing this negative enthalpy by this -2 is going to make a positive. So it's going to be times by 2, but it's also now going to be a positive number. So right here, we're going to draw a line like we would if we were doing an addition or subtraction. And we're going to times both of these by 2. So for A, we're going to have now 2 sulfur solids. I'm going to do it in a different color so you can see. 2. Now we're going to have 2 oxygens, which is a gas. And on our products, we're now going to have 2 SO2 gas. So now this matches with this one, which is good. But I know you're thinking, how is this going to end up like the final equation when it's on the wrong side? Well, we're going to get to that. When we do this reaction, reaction B, we're going to times it by -2. So the products are now going to become reactants, and the reactants are now going to be products. So we're gonna have 2SO3. Do it in a different color so you can see it. And now, that's the only thing on the products. So that's it for that side. Now we have to change these ones. So we're gonna have 2 sulfurs. And since we have a fraction here, if we multiply this fraction, 3/2 times 2, we're now going to have 3 oxygens. Because 3/2 times 2 is 3. Okay. So, what can we do now? This one, 2SO3 gas, is on the correct side. Good. Check mark. Now we have 2SO2 gas on the product side. Check mark. We're good. But how are we going to get our oxygens to be the same on our product side? And how are we going to get rid of these 2 sulfurs that we have? Well, as I stated before, on opposite sides of the equation and they're identical, so these are both sulfurs, making them identical, we can cancel them out. So since there's 2 over here and 2 over here, 2 minus 2 equals 0. So these sulfurs are now gone from this equation. Now we have 2 oxygens and 3 oxygens. Well, if we get rid of these 2 oxygens and take away 2 oxygens from here, 3 minus 2 is 1, so we're just left with 1O2 gas. So now, since we have our equation, and we can put everything together, we now have to figure out our enthalpy changes. So if, for reaction 1, we do the delta H, we have to times this by 2. So timesing this equation by 2 will give us negative 593.6 kilojoules. So it stays negative because we only times it by 2. A negative times a positive is a negative, so it stays negative. Now, with this reaction, reaction B, we times it by negative 2. So this enthalpy is going to be 791.4 kilojoules. And this is because we times it by negative 2 and it was originally negative. So not only does it double, that negative is gone. So now we can put together our final reaction. Our final reaction is going to be, we're going to look at this one. Only write the stuff that's left over and that wasn't canceled out. So we're going to have 2SO3 into 2SO2 plus O2. Now this reaction looks identical to this reaction, so that's how we know that we did it right. If you do this question and it in your final product doesn't look like the original equation you were given, something went wrong. So our question is determine the enthalpy change for this reaction. So we have the enthalpy changes for these 2 different ones, and we found them for when we rearrange the equations, but now we need to add them together to get it for this whole equation. These 2 are identical. So when we add these together, we get a delta H of 197.8 kilojoules. So that's how you do a Hess's law